Back to the channel. Today we're going to take a look at some electrical engineering problems and math applications for this specific job. First off, we'll look over some equations. First, this is the capacitor equation. This is a capacitor equation. It describes how a current through a capacitor changes as its voltage changes over time. This is the inductor equation. The inductor describes how the voltage across an inductor changes as its current changes over time. This is an RC circuit. It describes how voltage in a resistor capacitor circuit changes over time. This is an RL circuit, and it describes how current in a resistor inductor circuit changes over time. This is the RLC circuit, and it describes how the charge in a resistor inductor capacitor circuit behaves over time. This is the energy over power equation, and it uses integration to find the total energy transferred over a period of time. So, like when you charge your phone or you charge a watch, like that sort of stuff. This is a first. These you can see here, like a phone, MacBook, or like the chip. This is what electrical engineers do, and they make that. They make the memory, the graphics, basically the backbone. First, we'll start off with this question. A capacitor has a capacitance of 2F, and its voltage is V of t 3t to the power of 2. Find the current at t equals 2. First off, I'll start with the capacitor equation, which relates current to the rate of change of voltage, and here's the equation, I equals C dV over dt. Next, I'll differentiate the voltage function using the power rule over here. And if you still don't know what the power rule is, then you should check out the video above. Next, I will substitute the capacitance and the derivative into the equation, which is I equals 6t. Then I'll simplify to get the current of the function of that time, which would be this. So after I substitute that, I'll get 24a. So the next question we have here is an inductor has an inductance of 3H, and its current is I of t 2t to the power of 2. Find the voltage at t equals 2. First, we'll start off with the inductor equation over here, which is V equals L di over dt. Then I'll differentiate the current function using the power rule over here, which will give us 4t. So then I'll substitute the inductance and the derivative into the equation. I'll simplify to get the voltage as a function of time, and substitute t equals 2 into the voltage at that moment, which will be 24 volts. This is a picture of a capacitor, and this, of course, is a picture of an inductor. Next, we'll try something a little bit cooler, the magnetic flux equation. Here, we'll try something a little bit cooler, the magnetic flux equation. Now, this is used to find out the magnetic field when, for example, you place a piece of paper or an object between two magnets. So this equation right here is phi sub b equals BA cosine theta. Phi b is the amount of magnetic field passing through the surface. Phi b is the amount of magnetic field passing through the surface. B is the magnetic field strength. A is the area of the surface that the magnetic field passes through. And theta is the angle of the magnetic field and the normal. The normal is just the line perpendicular to the surface. So this is a picture, and it's pretty helpful to look at it. You can screenshot this if you want to, and screenshot the entire video. Next, we'll try a fairly easy question. I mean, It's not that hard, isn't it, right? So, a magnetic field of 0.5 t passes through a rectangular surface with an area of 2, m to the power of 2. The magnetic field is perpendicular to the surface, which means it's 90 degrees, and also means that that theta is equal to 0. So we find the magnetic flux. So over here we start off by using our magnetic flux equation. Next, we'll find that B is equal to 0.5 t, A is equal to 2 m squared, and theta is just 0 because it's perpendicular. So I'll just substitute all that in, which will give us 1, because cosine of 0 is 1, and 0.5 times 2 is just 1, so 1 times 1 is 1. So it's 1 Weber. Okay, thank you for watching this video. Hope you found it informative.